Hello everyone, this is Warda Ashraf. I'm an assistant professor at the University of Texas at Arlington. And today I'm going to show how we can produce low carbon and durable concrete by mimicking this ancient Roman technology. Our motivation is very simple. When it comes to concrete, Romans did it right. And based on this session, this seminar, most of us, we already know that our Portland cement concrete is not that environmental friendly material. It has a very high carbon footprint. Not only that, it requires us to use fresh water, and basically we consume 9% of global annual freshwater withdrawal. Also, the durability performance of this modern concrete is not that good. If we get 50 to 60 years out of our concrete, we feel very happy. On the other hand, Roman concrete, these ancient Roman structures, these are almost 2000 years old, still in a very good shape. So it's kind of a very, it's well known that Roman concrete is a highly durable material. But not only that, Roman concrete was produced using some raw material which has a very low production temperature. This type of Roman concrete, the raw material can be produced at around 900 degrees Celsius. In addition to that, Roman concrete, it can use poor quality of aggregate, and also we can, it doesn't need fresh water. We can produce this type of concrete using seawater. We need to keep in mind that for several locations in the world, freshwater scarcity is a growing problem, whereas seawater, we have plenty of it available. So considering all of these, Roman concrete, this ancient material, is kind of the perfect example of low emission and durable concrete. So it's a very interesting material, and we want to produce a durable concrete just following this ancient technology. Now, Roman concrete is a very interesting material, so there has been a lot of work going on to understand this Roman concrete, why it is kind of like showing this extraordinary durability. Now, there are some ancient books which are also 2000 years old. From those books, we can learn about the recipe of this Roman concrete. So basically, this is how they produce this ancient material. They use volcanic ash. In addition to that, they use slag lime, which they got after burning limestone. We can also find the ratios from those ancient books, and they mixed it with volcanic aggregates and seawater. So this is the recipe of those Roman concrete. And there are some very interesting publications from Dr. Jackson, who looked into the microstructure and reaction mechanism. And based on her research, it showed that when we mix these four ingredients together, first there will be a pozzolanic reaction which forms calcium aluminate silicate hydrate gel. But after that, due to the presence of seawater, it also forms some crystalline mineral phases, including some zeolites and aluminum chloride. And she suggested that these mineral phases, it has very interesting morphology like needles or plates. And these mineral phases actually responsible for this extraordinary durability performance. So what is our goal here? Our goal, now that we understand what is happening in Roman concrete and why it is durable, we want to mimic this process. We want to mimic this technology to develop highly durable, low carbon, and resilient concrete that we can use for varieties of structures. Our approach is very simple, since we already know that those microstructural phases are responsible for this extraordinary durability performance. Our first step, we will try to mimic similar macroscopic phases. And after that, we'll keep upscaling and ultimately reach the concrete performance level. Now, there are two major challenges. So most of the time when we talk about Roman concrete, we say it's a highly durable material, it has low emission. Both of these are correct, but there are certain limitations too. First limitation is the strength. Roman concrete is not actually a very strong material. It can, the strength is around 600 to 1500 pounds per square inch. This will not satisfy our current demand of high strength concrete. In addition to that, Roman concrete was produced using volcanic ash. We do not have enough volcanic ash in the US, so we have to find some alternative material to produce this, to mimic Roman concrete technology. In terms of raw material, there are some interesting publications showing the available raw material. So from this figure, you can see that we use almost 4,000 million tons of cement per year. There are alternative pozzolanic material that we could use to mimic Roman concrete, but we do not have enough amount available. The only other material that we have is clay, which can be used to produce Roman concrete. Again, clay has different types of mineral. Usually, kaolinite is the best one for concrete. However, we do not have a lot of pure kaolinite deposit in the US. Most of our clay deposit, it has impure or mixed minerals, and that's why we are looking at those natural clays containing mixed minerals. And clay by default is not reactive, so we have to calcine it around 700 to 900 degrees Celsius, and after calcination, it shows pozzolanic properties. So basically, this is what we did. We took those clay, we calcined it, and after that, we followed exactly the same recipe that we had in those ancient books to produce Roman concrete. Except in case of volcanic ash, we are using calcined clay. And we prepare this type of different shapes of sample. We look into the mechanical performance, microstructure, durability, and so on. Now, so this is the evaluation, like how our recreated system is going on. So one of the first tests we did is measuring the heat of reaction in the system. So we mixed calcined clay with Portlandite, and we added fresh water. And these are exothermic reactions. So if you see higher heat flow, that means there is a lot of reaction going on. If the heat flow is low, that means it's not that active. Now, based on this plot, what we saw is that when we prepare this mix using fresh water, there is actually not much reaction going on, as you can see from this flat line. However, if we add seawater, then there is actually some reaction going on. So it simply confirms that for this calcined clay and lime system, seawater is an activator. And that's interesting for us because, again, based on the previous publication, we know that for Roman concrete, seawater plays a very strong role. Our findings simply confirms it that yes, seawater is essential for this type of system. Next, we looked into the type of minerals that we form in this recreated system. So these are X-ray diffraction plots, and again, a lot of things going on. So we have lots of different types of crystalline phases. However, important is that we have similar zeolite phases, including Phillipsite, hydrocalamite in our system, which can also be found in ancient Roman concrete. In addition to that, we have the similar binding phase, that is calcium aluminum silicate hydride. Now, for this type of system, it's mostly we have almost 70% is amorphous and 30% is crystalline. So to understand the amorphous phase structure, we collected the NMR spectra, and basically this NMR spectra helps us to understand how the alumina and silica are arranged in this binding phase. And one thing we noticed is that in the gel phase, we have a lot of calcium aluminum silicate hydride gel, but in addition to that, we have highly polymerized geopolymer gel present in the system. Now, here is side-by-side comparison of what we had in the ancient Roman concrete, that is this right side figure, and it mainly had CASH and Tauber-Moret-like structure, chain-like structure. In our recreated system, we have similar CSH or CASH phase, but in addition to that, we have geopolymer gel, and we were expecting that due to the presence high amount of aluminum. The interesting part is that this geopolymer gel, even though it's kind of extra, it's not present in the ancient Roman concrete. This gel phase is also known to provide better mechanical performance. So our next step was to look into the mechanical performance, compressive strength. So here are the results. In case of ancient Roman concrete, usually we get around 600 to 1200 psi compressive strength. Again, as I mentioned, it's not sufficient for our modern application. But in case of this lime and calcium clay version that we recreated, we get almost 3 to 4000 psi strength within 28 days, and that is also at a relatively high water to binder ratio. So this type of material concrete, again, it can actually satisfy the strength demand that we have for our today's application. Again, the higher mechanical performance is simply because instead of volcanic ash, we are using calcium clay, which is richer in alumina, and that simply helps this type of system. We also looked into the durability performance, especially alkali-silica reaction. I remember that it's a kind of a problem in Maine because there is lots of reactive aggregate, and in those cases, if we use those aggregate, our concrete starts expanding, and at one point it cracks. And we did a standard test method. So in case of Portland cement concrete, once we use those reactive aggregate, there's significant expansion, and it simply fails the test, right? Because this is reactive aggregate. But once we use this recreated Roman concrete, we saw that even though we are using this highly reactive aggregate, there is actually no significant expansion. So somehow this material system is arresting the expansive gel formation. We still need to look into the microstructure, like what is happening, but so far it confirms that it has similar durability performance as that of our ancient Roman concrete. So that's all the experimental results I had. Some concluding points. Again, this presentation is just to remind you that our ancient Roman concrete is just kind of like a very good example of low carbon durable concrete. They prepared using volcanic ash, but we are showing that if instead of volcanic ash, if we use calcium clay, it can still be low carbon and durable. At the same time, it's satisfying the mechanical performance requirement for our today's application. So the strength is higher in this system. And of course, seawater is a crucial here. Seawater in case of ordinary Portland cement concrete is not a good thing. It causes durability problems. But for this type of system, seawater is helping us to gain the strength. So that's all I have for you today. Thanks to our funding agency, that is DARPA. And if you have any question, you can just send me an email here. Thank you very much.